when I was sort of cooking up some machinery since like my thesis, so I'll just talk about it. Okay, so take a Lagrangian in a compact symplectic manifold, and we say L is non-displaceable if sort of it intersects itself intersects every like sort of Hamiltonian push-off. And so in general, it's not known if like, you give me a general symplectic manifold, it's hard to sort of tell if there is such a Lagrangian inside of there. But in a lot of cases, you know of at least one. For example, so in complex projective space, there's this Clifford torus, which is sort of the given by like the moment fiber at the center of the very center of the moment polytope. So this is P2. Okay. And then so shows that that this particular torus is Hamiltonian non-displaceable by computing its Lagrangian Floer homology. Okay, so this is just sort of like an introduction and motivation for non-experts. So Fukayo, Ota, and Ono sort of developed this extensive program for toric, compact toric symplectic manifolds, and Lagrangians inside of them, which are moment map pre-images. And then so a consequence of this is that there's at least one orbit of the torus action that is non-displaceable in a general compact symplectic toric manifold. But sort of in the other direction, you have like this, this result by McDuff and a further result by her and some other people that show how to displace like a lot, maybe not most, but like a lot of torus orbits. So for example, like in the monotone toric case, when dimension m is less than 6, you can displace all but the single guy that was shown up here. So can you sort of find continuous families of non-displaceable but non-Hamiltonian isotopic Lagrangians, let's say in the compact setting? We saw an example yesterday in Elsa's talk. So in general, it's hard to show sort of non-displaceability due to difficulties in defining and computing Floer theory for non-monotone Lagrangians. But somehow yesterday, those examples were monotone, and that left shift vibration. So the most computable situation for Floer theory is sort of in the toric case. Excuse me. But so sort of the examples in the literature seem to all involve more sophisticated techniques. So let's just sort of mention some of those. One of them is sort of this result by Fu. So there's uncountably many sort of pairwise disjoint tori in the product of S2 with itself that are non-displaceable. So in particular, they're non-displaceable and pairwise disjoint, so they're not Hamiltonian isotopic. And none of them are equivalent to the sort of product of two equators. Right? And then so they give sort of more examples in like some blow-ups in 4 dimensions using like these bulk deformations. And then so Vianna generalizes this above construction here to sort of multidimensional families and even products. And moreover, sort of Tokanov and Vianna sort of give one parameter families and these two guys, and also sort of these intersecting families in del Pezzo surfaces where sort of like one torus from one family intersects all of the other guys, but they're sort of within each family, they're not Hamiltonian isotopic. Did I interpret that result correctly? Oh, I guess he's not here. Okay. Hi. Okay. So, and then so, I think this is the last one I'm going to give. So, in the not smooth case, you sort of have Wilson Woodward sort of show that there's like a sort of open set in the of actual moment tori in the weighted projective space. So this is like the quotient of of P2 by some finite group action. And they call it like, they use like this thing called quasi-map Floer theory, or I think you can also call it like gauge Floer theory or something. Basically, Floer theory for like reductions and nice quotients. And here I'm saying that non-displaceability means that non-displaceability upstairs among the class of invariant Hamiltonians with respect to the group action. Okay. Okay, and then I guess I should mention sort of one more that I could think of. Is sort of in flag manifolds, there's like a sort of long string of people where it sort of culminated with this like Cho Kim Oh paper where they show like an existence of line segments of sort of non-displaceable torque by sort of considering a very special integrable system and then applying like torque techniques. Okay, so we're going to give sort of an example of like an n-parameter family in a n plus k real-dimensional symplectic fiber bundle. And sorry? Borman? Oh, okay. What year? Okay, thank you. Cool. Okay, so I mean, really, it's just sort of an excuse to show off some machinery, but it's like a neat little thing. So we have this like sort of n plus k real-dimensional symplectic fiber bundle. Oops, 2n plus 2k real-dimensional symplectic fiber bundle. And so I'm not really thinking of a Lefschetz fibration, like literally a fiber bundle where the fibers are all sort of non-singular. So the construction. So I guess the simplest sort of thing you can do is take like a projectivization of a vector bundle over complex projective space. Okay, so let sort of O1 be this hyperplane, this holomorphic hyperplane line bundle over Pn. So it's sort of the dual to the tautological line bundle. And let O of I denote its like sort of I tensor power. And then so you can sort of form this fiber bundle where you take like direct sums of line bundles and you projectivize along the fibers. Okay. And then so we're just going to assume that these integers in here are non-negative. Okay, and then so these might look familiar for k and n equal to 1. These are known as the Hirzebruch surfaces. And then so you can put like a toric symplectic structure on this space by sort of considering a lift of the Tn action and then also like a Tk action in the fibers. And like you would consider like the appropriate moment map with polytope. But we're going to sort of think of something a bit more flexible and consider it as like a symplectic fibration, sort of according to this like Gilliman-Lerman-Sternberg theory that I will review shortly. And by shortly, I mean in the next slide. So to sort of put like a symplectic form on this fiber bundle that you can, how do I say, that you can sort of vary but not vary too much, if that makes sense. Let's say you can put a Hermitian metric on each of the line bundles that is compatible with the holomorphic structure. And then you sort of get this churn connection associated to each of these Hermitian metrics and complex structures. So this is sort of the analog of the Levi-Civita connection for like a Riemannian metric. And it doesn't necessarily have to be this connection. It could be some symplectic connection. So you get sort of this induced like TK connection on the fiber bundle. And it doesn't have to be flat. So more precisely, when I say connection on the fiber bundle, I just mean sort of a splitting of the tangent space of the total space. So you have sort of F is the fiber, and X is total space, and B is the base. TF is well defined as like the kernel of the derivative of the projection. And so the splitting is sort of picking the H, and that's going to sort of prescribe parallel transport along curves in the base. Okay. Okay, so right, you have all this stuff. So can you sort of find some sort of symplectic structure on this total space that like gives you this connection in some sense? So that's sort of translated to something precise. You know, you want like a closed two-form A that, like, when you restrict to the fiber, it's your favorite sort of symplectic form up to Hamiltonian isotopy. So in this case, the fiber is PK with a Fubini-Studi metric, or form rather, and such that it's a connection form. So like the perp to the tangent space of the fiber with respect to this form is going to be H. Okay, and then so the answer is yes. I mean, it's yes in this case, and it's yes sort of in general if F is compact and simply connected. And parallel transport in H is a symplectomorphism. So the holonomy around some loop is always a symplectomorphism. And so the construction of that, okay, so for any closed connection form A, for symplectic connection, you sort of have this curvature identity. Yeah, let's not do that yet. So if sort of holonomy with respect to the connection H is a symplectomorphism, and F is simply connected, it's going to be Hamiltonian. And then so you can, so this is basically from Gilliam and Lerman Sternberg's book. Sort of the curvature here, so this is like I lift two tangent vectors from the base to the horizontal distribution. Okay, and I take their Lie bracket, and there's going to be some remaining vertical component that doesn't lie in H. And so that's like the curvature. So I project that onto the vertical part, and I want to see if that's like that turns out to be like a Hamiltonian vector field for the fiber. Okay, so this is mod H, where you sort of insertion here for a vertical vector is the same as insertion over here. And then, so this is true for any sort of connection form that's closed and generates the connection. So that tells you that sort of the Hamiltonian for the curvature vector is sort of, you know, this guy. So you can say normalize and define. So A, you already sort of know that it's defined, you know, what it's supposed to be vertically, and also it's supposed to be like what it's supposed to be like vertically, 0. And then so sort of on the vertical distribution, you would define it to be this unique zero average Hamiltonian for the curvature. Okay, so I mean, you can just sort of think that this is more just like detail for people who might be curious. You can just sort of think that there's a closed two form that generates the connection and sort of has like a normalizing condition. Okay. And then sort of more generally, the answer is yes, you can remove the simply connected fiber assumption as long as the Hamiltonian, or as long as the holonomy around any closed loop in the base is Hamiltonian. So that's, I couldn't find the paper for that. I mean, I found it in McDuff-Solomon. Okay. So this is called the minimal coupling form. And then so finally, so you know, you might have some sort of degeneration in the horizontal direction. So you can sort of take a lift of the form from the base, since Pn is compact symplectic. And you sort of multiply by a large enough value of k so that sort of in the horizontal direction you don't have any sort of degeneration. Okay. And this is a symplectic form. And then so you can get like a lot of sort of symplectic forms this way, but they don't differ too much. For instance, you have this theorem. So if the fiber is simply connected, then sort of for any like sort of symplectic connection you pick on your total space, the cohomology classes of the minimal coupling forms are going to be the same. And then you can sort of use a Moser type argument to say that these are symplectically isotopic for large enough K. Okay, so yeah. So are there any questions so far on this sort of stuff? Okay. Okay, and then so in this context, you could think of sort of the most naive way to construct a Lagrangian, which is just like a fiber subbundle sort of sitting in there. And so you have like a Lagrangian in the fiber and a Lagrangian in the base, and you can sort of imagine a section here, a section of LFs over LB. Okay? And then they sort of have to basically maybe you can try to imagine something like that's to be a Lagrangian in the total space, you need sort of to be invariant under parallel transport along LB, and that there's like a sort of fiber where this weak coupling form is sort of 0 along the tangent space to LF, and also along sort of this horizontal distribution restricted to L. And we're going to give like a sort of construction later. I guess it's sort of typical in the situation. And then so main theorem statement. So let sort of K times delta be this the moment polytope for KPN. So it would just be like sort of the n simplex just sort of scaled by K. With this moment map sort of scaled by K. And then so I'm thinking of like a little sort of neighborhood in the moment polytope, sort of surrounding the Clifford torus. And R is sort of small. How small I cannot say. So this lies in the moment polytope. Okay, and then so there's a theorem / example. There's a weak coupling form on the total space of this projectivized vector bundle, and a pairwise disjoint family of fibered Lagrangian tori that are Hamiltonian non-displaceable, and sort of lifts of each moment torus in this neighborhood here. So it's sort of parameterized by this little ball. And each L in the family, it's just going to be a lift of like a nearby moment torus to the Clifford torus. So I say here parameterized by projection composed with moment map over that neighborhood there. Can people see that? This chalk is bad. So sort of parameterized by points in here. Okay, and then so I have to tell you how to, I have to tell you how to construct this. And then I have to tell you why they're Hamiltonian non-displaceable. So the first part is the easy part, and then there will be the Floer theory part, which then the non-experts can like take a nap or something. So the idea, and it's not very, I guess the construction in itself of the Lagrangians is not that interesting, but it's more like what you have to do. So over sort of this toric neighborhood, you can sort of trivialize the bundle to some extent using some general theorems. And they're just going to be products of moment tori. Okay, so you can sort of consider a lift of the torus action to x, so the Tnx on the base. And then sort of you have this this sort of theorem that says for the weak coupling form that you might have picked, you sort of have projection, and here's P n, and here's sort of image of moment map. So here's the moment map for Tn. So for the weak coupling form that you might have picked, yes? Oh, so bigger? Yeah, okay, thank you. Okay. So you have moment map for Pn, and you have this like torus action down here. You're considering a sort of lift of it to x, and this is pi. So for the weak coupling form that you might have picked, it's not necessarily true that this lift of this Tn action is going to have moment map this. But you can sort of adjust the connection in this little small neighborhood here. So we're sort of adjusting the connection here so that the moment map for the Tn action on the total space is this project and then take the moment map for the base. So it sort of allows you to trivialize the symplectic fiber bundle over each of the moment tori in the base. And then you can sort of bootstrap this to a trivialization over sort of a neighborhood of tori. And then so the family is just going to be sort of the product of something moment here. So x. So this is P alpha 1, alpha 2. And these are the moment map coordinates. And then you say, so I'm thinking sort of P1 over P2 right now. And then so this is P1 in the fiber. And then so this is Clifford. So basically taking a product of some moment torus nearby the Clifford torus and the Clifford torus in the fiber. Okay. And then so this is, we're going to have to adjust this, to actually get the result. But are there any questions so far? Okay. Okay, so sort of detect non-displaceability for these guys. We use sort of a Lagrangian Floer theory for symplectic fiber bundles. Floer theory, in this sort of sense, has like in different flavors. It's sort of like a minor trend, maybe over the last 10 years or something. And I found a way to compute it to some extent, really. Okay, so we're going to recall some stuff. So assuming proper transversality and compactness results, you can associate an A infinity algebra to some Lagrangian. So let's consider the Novikov, universal Novikov ring with coefficients in Z2. Okay. So you have exponents here, which limit to infinity and can be 0. Okay, and then so pick like so we're going to sort of consider these like Pearly Morse trees. So pick like oops, this is general, okay. So pick like a Morse function on your Lagrangian that has sort of like a unique co-index 0 critical point. So like basically I'm thinking it has a unique representative for the Poincare dual of the fundamental cycle. And then you have this sort of lambda module. which is generated by these Morse critical points. Okay? And then you can sort of attempt to define an A-infinity algebra structure on this by using sort of these tree disks, as in Cornea Lalande and Buran cornea. And so you pick a local system, like we've seen so far, which is a representation of pi1 into the group of units of the Novikov ring, and sort of let this guy denote the holonomy evaluation around the boundary of some disk class in H2 and some relative disk class in H2 x comma L. Okay. And then so you sort of try to do this to some desire. So you define like these, at least on Morse generators, you define sort of the product of x1 through xn, the nth product, to be sort of some count in some moduli space of holonomy of sort of outputs weighted by holonomy and t to the what would be the symplectic area of the disk guys. Okay, so I'm basically counting these things early Morse trajectories. So these guys are holomorphic disks with boundary in L, and these edges are going to be gradient flow lines for negative f, and sort of marked points on the boundaries of some of the disks. So this is going to be required to live in the unstable manifold of x1 with respect to negative f. And this is going to be same over here. And then in this direction, so these guys you can call the leaves, and this is the root. And this is going to be in the stable manifold of x naught with respect to negative f. Okay, so that's basically all I'm going to say for that. So Perley Morse trees, and then sort of you have to only consider certain ones that satisfy this like virtual index formula, which is based on the Maslov indices of the disks and some nodal conditions on the disks between themselves. Okay. And it turns out you can sort of, you can actually make sense of these products among like a specific class of perturbation data that's sort of adapted to your vibration. Okay, so first off, so you have this sort of Morse data. So you can kind of consider Morse functions f that are sort of the sum of two Morse functions. So the b is going to be some function on your base Lagrangian. And you can pull that back, and it's not going to be Morse anymore. So for instance, so you have maybe height on torus. Is that big enough? So like here is a critical point of B, say. And then I'm thinking about, say, a circle up here. And then, maybe that's not a critical point, so I'll draw a circle instead. So that's also a circle. And then you can sort of put some function g on the total space where you restrict to each of the critical fibers. So this guy here is something I'm interested in. So g on that is going to be Morse. And you can extend this sort of by 0 and sort of make sure that the derivative of g doesn't sort of overcome the derivative of b, so it stays sort of Morse. Okay. Let's not get to that yet. And then so I should tell you sort of about some almost complex structures. So if you sort of have a JF on F tamed by omega F exists, okay. exists unique J, so on the total space, such that, so it's going to, let me start this over here. So this is sort of it's like sort of implicit in like Gromov's paper from 85. So there exists unique J ACS on Tx such that, so you sort of have one, if you pick the J sort of on the kernel of pi, or like a section of almost complex structures, then you can sort of say J restricted to the fiber is that, so T F and 2. So J preserves the connection. And then 3, pi is holomorphic. Is holo. So with respect to, you have to input a JB. On B. So tamed by the form there. Okay. Okay, and then so you sort of have like a nice starting point to get off the ground with Floer theory for this sort of situation, mostly because of this. But these are sort of nice features. Well, this as well. Okay, and then so say that a pair is rational, a symplectic manifold and some Lagrangian sitting inside of it. If omega b lives in cohomology with rational coefficients, and the symplectic energy spectrum of disks and spheres and sort of this, or stuff in the image of the Hurwitz morphism is discrete. Okay? And then so you can sort of get off the ground with just sort of varying these 3 parameters here and these sort of 2 guys here, these Morse input data. So if you have sort of a symplectic fiber bundle and a fibered Lagrangian where the fibers are monotone and the base is rational, then there's sort of a co-meager set of adapted data along these lines. This is the abridged version, such that these A infinity maps make sense, and they said A infinity maps make sense, and they actually satisfy the A infinity axioms. So it's just like perturbing within like maybe more of your favorite class of almost complex structures instead of something more. Okay. So great, you can sort of fly a little bit. And then so computing, how much time do I have? Until 50?
Like 20 minutes.
Okay. So sort of the actually computing for this particular family that we constructed. It's going to be sort of the same that you might see, but you have to sort of know how to write down some things. So you compute the leading order potential, or the leading order terms of the 0th A infinity map, which is known as the potential. And you show that it's a multiple of this. This is going to be the unique representative for the Poincare dual to the fundamental class. Okay, and then so like we've sort of seen in the summer school last week, and in general, okay, so say L is weakly unobstructed in this case. So sort of typically in this situation, you can sort of arrange, you can do just like sort of mild deformations of the A infinity algebra so that you actually get that mu1 squared is equal to 0. Okay. And then so you have like a homology theory based on that chain complex and this differential. And then so sort of a theorem that you can, or an idea you can apply, which I think maybe it goes back to Fu, is this following sort of principle that if you sort of take the derivative with respect to the representation of the potential, then that's sort of the same as evaluating the differential on that thing. And that thing, it just sort of, it happens that the space of representations, or these local systems, the tangent space to that is the first Morse cohomology. If your sort of L is, like if the cohomology of L is like, say, free in this case, and finite dimensional. Okay, so this says that if you have like a critical point of this guy, this 0th order guy, then the sort of, there aren't going to be any Fleur input, like Fleur sort of counts for Morse 1 cocycles. Okay, so then you can sort of bootstrap this if you're dealing with a torus whose cohomology is generated by 1 cocycles. So if L is like a torus, like in this situation, it's weakly unobstructed, like I mentioned in 1, then one can show that you sort of have this for all Morse cocycles, that the sort of Fleur differential vanishes once you sort of, only consider, once you sort of take like the 0th order part of the Fleur differential, which only counts Morse trajectories, at a critical point of the local system. So using this fact. And then you have sort of this thing from that. You have that, like this Fleur cohomology is just going to be all of the sort of Fleur contributions to this new 1 cancel, and you have this isomorphism. Okay, and then so, as I'll mention later if there's time, that this is sort of the rank of this guy over lambda sort of forms a lower bound for the number of intersections of L with some push-off of itself. Okay, so if you have this, then you can show that it's non-displaceable. Okay. And then so finally, so this is great and all. So to ensure the existence of critical points for each L in our family, we're going to have to sort of deform the connection a bit to sort of get these like disks that appear to sort of match up. Okay, and then so how to do that? So let's define this cal W n as the, say, sum of the n lowest order terms, order I mean order in T in the potential for each Morse generator. So you have like this finite dimension, this finitely generated module over lambda, and then so for each generator I sort of cut off after so many degrees of T. And this is well defined since in this case it's going to be rational. So you sort of have discrete in some sense. And then so it's just sort of, you can sort of solve for a critical point of the potential by sort of considering some non-degenerate critical point of this sort of leading order guy and like applying like an implicit function theory and argument, or just sort of solving order by order sort of up the chain of T. Okay, and then so how to compute this? So in practice, it's sort of easier just to do the low area guys. So let's just assume that X and L are fibered as above, so it's compact, and the fiber is monotone, and the base is going to be rational. So the structure group of X is some finite dimensional Lie group that X by Hamiltonians on F. And then so this action, so we're assuming all of this. So the action extends to like a sort of complexified group action. for which there's like an invariant integrable on this complex structure. So in our situation, you have pk, and we're thinking about G is the k torus, and then so GC would be C star to the k. And sort of this sort of standard complex structure is also invariant under the C star to the k action. Okay? And then so this is sort of also important. You need sort of L to be like ambiently a product. And it's quite hard to remove this, actually. So sort of L is trivial via some ambient symplectic trivialization over the base torus. And then so this sort of allows you to write down like a map between zero-dimensional moduli spaces that takes configurations in the base with boundary in LB to things that sort of contribute to the potential for L. And moreover, you can sort of argue that the lowest and second lowest terms, so sort of for like small enough fibers, come from, okay, so let's explain this. They come from lifts of the first order terms from the base. So maybe I'll draw a picture. And then if you recall, this is sort of, I didn't write this down. It's just like sort of a, I don't know. So you have a potential, or leading order potential for the fiber Lagrangian sitting inside F. And I'm just thinking of configurations there, just sort of include it into the maximum of the base Morse function. So sort of stuff like on this picture. So you have maybe a disk with boundary sitting here. And the L, so here's my critical points here in the fiber. And the L is going to do something like lift, so the output is here. This is no input and one output. So the output, it's going to sort of lift it to the top of the fiber. So this is U, and this is LU. And then also you have these sort of, so this is, say, this is P1 here. And you have these sort of disks sitting here. This is like the maximal. This is max B. Okay, so the sort of in these, if you assume these sort of strict conditions, you can actually write down what like the first two terms are. And it's sort of, you can sort of compute from here. So let's restrict to the case of, say, a P1 bundle over P2. Okay, and then so according to our theorem, the second order potential is this guy here. So this is the fiber term. So this is like the potential for the Clifford torus sitting in P1. And it's going to be a multiple of the maximum. So this here, let's use pink. So this here is XM. Because it's monotone. And you can sort of, the standard integrable complex structure is regular in this case. So you can just sort of write it down. So this is Cho O, or actually Cho, but eventually. This here is the potential for a moment torus in P2. And that's Cho O. So these alpha I represent the area of disks of this form here. So let's draw another picture. The alpha I are like the moment map coordinates. So maybe I'll draw it slanted, because for some reason I think of it slanted. I don't know. So So sort of you have alpha 1, alpha 2, and then so these disks are sort of lying in these fibers here, and then you have a third one here. So by like sort of the fact that it's a homogeneous Lagrangian, for the standard complex structure, these disks are actually regular, and you can sort of count them for an invariant. And then I said it was the minimal, it was sort of the lowest order term, so you have to take the minimal term here, or like the guy who has the lowest order degree, the guy who has the lowest T degree. And you're sort of assuming that sort of the area of these disks is large enough to sort of overcome the fiber area. Okay? And then so you can see from this, it's sort of unobstructed. Joe, oh, yes. It's a multiple of this unique coordinate zero critical point. So you can sort of take for a cohomology of this, except there's sort of a problem. So I have 10 minutes, okay. So sort of a comment, I'm sort of assuming that you don't gain or lose any area when you lift disks. That's what I wrote here. So these are the same as the areas of the disks in the base. And then so sort of over like the pullback, so you sort of have the UI, let's just say this is U1. The weak coupling form becomes exact, basically by this theorem that I showed you before. So you have like the trivial connection, and then you have the pullback connection, and they're supposed to be of the same class. And then so that sort of you can define this sort of vertical area as the integral against the so u tilde is some section. So let's say we lift ui, and we're just taking sort of the vertical component. So u tilde is some section of the pullback, and you sort of contract it with the weak coupling form. And then so you get like this term here, which represents sort of a disk sitting in F with boundary LF of some class. And you get this sort of holonomy term, which is sort of just depends on the boundary by Stokes' theorem. Okay? And then so I'll just sort of explain very quickly. So so parallel transporter around some moment torus in the base. And this connection, well, it's actually the trivial connection. But in general, it's just like a linear torus action, a linear Tn action on Tk, which has to reduce to the standard torus action. And since we're assuming that sort of this H is like a sort of zero average Hamiltonian for parallel transport, and LF is a Clifford torus, it vanishes. So this term here is 0. And then so the properties of this lifting map between modular spaces sort of allows you to pick out sort of this vertically constant class in the pullback. Yes?
Why is Lagrangian product?
Because, yeah, that's a good question. So like in general, like if I try to like lift a disk from the base of the fiber, you might either gain or lose a Maslov index, or 2 or 3 or 5 or 6. And also, like when you project, you might gain. So there's no sort of correspondence between potential for the total space and potential for the base.
But I mean, the Maslov 2 disks upstairs still come from some Maslov disks downstairs.
Yeah, right. I mean, that's sort of what I'm working on now. Yeah. Yeah, it's just like a matter of like figuring out what it is. Yeah. Okay, so the sort of area remains the same when you sort of lift it to the total space. So the problem with this formula unless like sort of you have that alpha 1 and alpha 2 are equal to k over 3, so that all these t terms are the same, you're not really going to find like a non-degenerate critical point of this guy. And I'm not doing the computation. And this is sort of most likely the sort of low order potential that you might see if you say applied like this sort of foo program to by viewing the space as like a toric manifold. Okay. So if you want to get sort of non-displaceability for this family, you're going to have to sort of modify the connection a bit so that you have these UIs in the base, and when you lift them, sort of you pick up or drop off the appropriate area to sort of make these guys sort of match up. Okay, and then so this is a sort of so you have like a sort of a function value of one form that takes tangent vectors on the base and spits out some function on the fiber that sort of prescribes the infinitesimal parallel transport in like the v direction. And you can sort of modify the weak coupling form by this. So you have so AH plus K pullback is what we had before, and then you sort of take this sort of exact guy, and then phi is just some cutoff function that cuts off outside of the small neighborhood of the Clifford torus. You say it again. Yeah. The Lagrangian. Some bulk deformation, you said? I'm not sure. Yeah. It's sort of like I mean, you can sort of do like this Moser argument to sort of get back to where you came from, since it's exact, and you sort of shear things a bit.
So, let me rephrase that.
Yeah.
This modification that you were doing, what's it doing with the disks that live on the fibers?
It's not doing anything. Yeah.
This is not doing anything.
Right. Right. It's still. So you can take sort of delta to be this, and so there's sort of no fiber directions showing up. You have sort of, so you pick like this sort of H. So sort of I'm not really modifying the sort of each fiber. It still agrees. I'm just sort of tilting the connection a bit.
Okay, but are you not somehow compute, say, this deformed symplectic area that is you're evaluating on disks with boundary disks that live on the fiber
Uh-huh.
over in your Lagrangian?
Yeah.
What does it do with respect to
This that live on the Lagrangian fiber. It's like a. I'm trying to think. So like it's sort of like to sort of deform this back to the. Yeah. Okay. So I guess the. Let me think now. So you can sort of like relate this back to the old form by like a. By sort of like a shear that sort of has like, so in this picture over here, it's sort of gonna like sort of shear and like sort of keep keeps like the sort of circles along the map intact, but it sort of moves them a bit. So it's going to be area preserving. Yeah. I mean, it really shouldn't change it. I mean, I'm not using like a sort of like sort of I don't know. We can talk after if you want. Yeah. So I'm thinking of taking like this sort of zero average H. So you have P1. And sort of the value here is some sort of maximum. Okay, so you sort of shift it so it has zero average, and then the Clifford torus sort of lies at a maximum. So it's still Lagrangian with respect to this form. Yeah, because if you take D of that, you get DH is 0 on Clifford of the fiber. Okay, and then so these are the moment coordinates, and these are sort of the angle coordinates in the base. And then so you have to sort of check that it's the Lagrangian, and then you sort of adjust R and the cutoff function so that you have sort of then you still have a symplectic form without changing K. And then so the area of the lifted disks are sort of modified by this. So you started with alpha, and then you have to sort of integrate over H around the boundary by this Stokes theorem guy, and you get K over 3 for, say, the first two. Then the last two, you sort of get this sort of, it's along the diagonal in the base. And you have a change of sign since it's going the opposite direction. So you get K over 3 again. And then so, I guess I'll just sort of finish up. So these sort of, the theorem that I stated doesn't quite work. You have to sort of trivialize the bundle over, like, say, a pullback of a larger disk. But you sort of argue in the same way. The modification is like not so extreme that it still sort of works. And then so sort of for each an L in the family, you have something like this, where they're all sort of equal with respect to this modified symplectic form induced by the new connection. Okay? And then so sort of in this case, you can find like a non-degenerate critical point with respect to the representation. And by this sort of general argument that we had before, you have that the Floer homology of this guy in our family is just isomorphic to the Morse homology, some representation. And then so in general, you get sort of the same thing. So I mentioned this earlier, I might as well just state it. So by using sort of like a PSS type isomorphism defined in this context with sort of your typical Lagrangian intersection Floer cohomology, you get this sort of rank bound, which shows that each of these L's is non-displaceable. Yeah. So I'm going to stop there.